Let's take a look at the computational formula. The beautiful thing about the computational formula is that it doesn't involve the mean. And that's especially helpful if the mean happens to be a jagged number, a number that's not a whole number. So the sum of the squares there, sum of squares abbreviated as SS, is also equal to the sum of all the values squared minus the sum of all the values that is then squared, as we spoke of before at the end of chapter 1, going back a ways, divided by capital N for this population. Let's take a look at this very same array of numbers, and you'll notice that the sum of squares arrives at the number 22. So I've got 1, 0, 6, and 1. The sum is 8. I square each of those values. So when I square them, I get 1, 0, 36, and 1 for a total of 38. And then I can undergo this formula. The sum of squares equals the sum of all those values squared, which is 38, minus the sum of all the values that is then squared. I don't know, it's hard to articulate that, but you can see the difference there. When I put it in parentheses, I add the numbers first and then square them, and that's 8 squared, and then divide by the number of numbers, which is 4. So 38 minus 64 over 4. 38 minus 16, that's 22. It arrives at the same number irrespective of what the numbers are and what the mean is. Now, why would you go about this way when you could easily do what we call the definitional formula? The chief benefit here is that if we have a mean that's 2.17 or 6.03 or something like that, it becomes harder to deal with the mean, subtracting from each number and then squaring it. This allows us to get around that, to circumvent it completely, and some see it as an easier approach. So my population variance, and again, for the time being, we're speaking only of population variances and standard deviations, is represented by the symbol lowercase sigma squared and equals the mean square distance from the mean. The population variance is obtained by dividing those sum of squares by n, and the standard deviation is merely that square root. So the variance is the sum of square divided by n. The standard deviation is the square root of that. And there's another couple of expressions of the formulas there. There's my population standard deviation, which is merely the square root of the variance. And again, that variance is indicated by lowercase sigma squared. The square root of that is the standard deviation. So I'll do my best to express these formulas in the simplest way possible, of course. Let's take a separate array of numbers. And we've seen these numbers before, actually, at the end of chapter 1. 10, 5, 2, 0. In this case, let's consider what the mean would be. Sigma x equals 17. If I divided 17 by 4, that's 4.25. That's not a rounded number. That's not very convenient. So I might go ahead and do the computational formula. So I've got 17 there, and then when I square each of the numbers and then add them up, I get 129. And then when I square 17, I get 289, which you knew off the top of your head. I'm kidding. That's why we have calculators. So computational formula for sum of squared deviations from the mean. The sum of squares is sigma x squared minus sigma x in parentheses squared over n. 129 minus 289 over 4, which is kind of a clunky number, equals 129 minus 72.25, 56.75. Okay. Well, that came out pretty easily. I mean, it wasn't the easiest thing in the world. But let's say I wanted to put myself through the mild heartache of doing it the other way, of subtracting the mean from each number. This would be the definitional formula for the sum of squared deviations from the mean. It's just a little bit more complicated practically because of the square decimals. So I subtract 4.25 from each number and I get 5.75, 0.75, negative 2.25, negative 4.25, and then I've got to square that spaghetti, right? And of course, by the way, before I go any further, I want you to confirm that the sum of all those deviations, the sum of all those subtractions is 0. And sure enough, it is. But then when I square 5.75 and 0.75 and negative 2.25, negative 4.25, I get some jagged numbers. Now, for the sake of being exactly accurate, I took them all out to the 4 decimal places. I really wanted to do that because I can demonstrate then that the sum of all of those lengthy numbers is indeed 56.75. It's the same. Now, the drawback of this, of course, is that carrying out all those decimals. Now, some students don't care they're happy to do that, and they actually prefer this formula, irrespective of carrying out the large decimals. Then, may I calculate the variance? Sure. That 56.75 divided by capital N is 14.19. And then for the standard deviation, just lowercase sigma, is the square root of that 14.19, and I get 3.77. So in isolation, that doesn't mean a tremendous amount to us now, but we'll certainly begin to visit what that standard deviation means in more detail here shortly.